This talk is harder, better, faster, stronger semi-auto vulnerability research. If that's not the talk you were expecting to be, stay here anyway. It'll be good. Lurene Grenier manages the analyst research team for SourceFire and is also an active developer on the Metasploit project. Richard Johnson is the primary research engineer also at SourceFire. So, guys.
Turn myself on here. There we go. Can everyone hear me? Excellent. All right. So we're in the programmatic track. I guess, is there a fuzzing track? I think there is, right? I haven't even looked at the schedule. I'm going to assume so. So we're not here today to talk to you specifically about fuzzers. And we are not here today to talk to you specifically about tooling, although fuzzers and some tooling are going to feature pretty heavily today. What we are here to talk to you about is industrialization. Okay? So right now in vulnerability discovery, we've kind of got two ends of the spectrum, right? We've got people who are digging through code, doing reverse engineering, or fuzzing to find that very specific, unique snowflake of a bug that works for them and makes them happy, and they can develop to an exploit and make somebody look bad or whatever else they feel like doing with it. On the other side, we've got people who are finding tons and tons and tons of vulnerabilities, not having the time to give them the attention that they deserve, toss them on a thumb drive, handing them out to people, doing whatever, giving them to vendors, right? But we want to kind of go the other way around. So what we'd like to do here is find a whole bunch of bugs and then give them all the attention that they deserve, kind of in an industrialization type of way, right? So when people started building cars, they would build an individual car, they'd sell it to a single person, they'd go back and build another car. How many orders they got, they didn't know. How many cars they were going to build in a set amount of time, not really sure. They were nice cars, but they're only building one, right? What we'd kind of like to do here is add sort of an assembly line around our fuzzing process, our bug discovery process, and turn each of those bugs into a BMW, which is, of course, mass-produced, but it's still worth 40K, and it's going to make somebody very, very happy at the end of the day, right? So where are we right now? Currently, we know that finding bugs is not the problem. Fuzzing works. Everybody knows fuzzing works. Everybody's finding bugs with fuzzing. You can find bugs with very simple, very stupid fuzzers. You can find bugs with very complicated, generation fuzzers, like Microsoft's bugs there, like JS Fun Fuzz, which is, pretty intelligent. So you can find a whole ton of bugs. That's not a big deal. Okay. We have tools to work on this problem. We have distributed fuzzing. People have done this before. And we have pretty solid crash analysis. Right now, you're seeing a lot of taint tracking stuff come up. You're seeing a lot of tooling around the triage side, right? But our main problem here is that we have no workflow. We have no process for doing this, okay? And what we'd like to do here is apply a workflow to both generation and, more often, dumb fuzzing, so that what we end up with is a consistent flow of vulnerabilities, and we save human time doing it, okay? So that's our primary goal, okay? We want to have a full pipeline, okay? So we're not coming at this from the standpoint of a vendor who creates software, who needs to find all the bugs in their product to be secure. And we're not coming at it from a researcher who needs to find one or two very interesting bugs to kind of add to the what am I looking for? The zeitgeist, right? To push things forward. What we'd really like to get here is a consistent flow of vulnerabilities that we can consistently exploit for cash flow to attack a target. And the targets that we're looking at are dictated by the marketplace and by the environment. Okay? So our secondary goals are pretty simple. Okay? We need to know something about that vulnerability, so there's going to have to be some triage afterwards. And we want to have a good human time efficiency rating. Okay? So we don't want to waste people's time doing this. We've got a limited workforce, and we want to make sure that they're working efficiently to get what we need. So I can find a whole bunch of very interesting bugs that take a very long time to triage and a very long time to exploit, and I can hand them to my exploitation team, and it's going to take them a long time. They'll get them done, But those are really bad ROI bugs, right? They're not the bugs that are going to get us the cash flow we want, get us in and out of enemy systems the way we want, okay? Secondarily, we want to have some CPU efficiency, and we have to have some ease of use, okay? CPU efficiency, very much secondary to human efficiency, but we'll see in a second that it's still very important in bug finding. So this is going to be our basic workflow. And as you can see there, we've got 3 in gray, attack surface analysis, input selection, fuzzing, okay? And those are separated from our triage set. And one of the things that we think is very, very important here is to separate that triage from the bug discovery, okay? Right now, you'll see a lot of people saying, 2 years ago, I fuzzed such and such a thing, and I found no bugs. That doesn't make any sense to me because it's a singular action, I fuzzed, right? What you have to do is continuously fuzz all the time and separate your bug triage from that. So it's not like you fuzz and then you triage. You are always fuzzing and you are always triaging, okay? So what you'd really like to see up there is kind of a circle of attack surface analysis, input selection, and fuzzing, and triage is a separate thing done by a separate group of people afterwards, okay? And what we're going to try to do is figure out what we need to do to facilitate that continuous cycle of fuzzing and facilitate the separate triage from a different group. Okay. So as has been pointed out a few times, the most important factor in our bug discovery is going to be our input selection, right? We don't want to have fuzzing be an active thing. It's got to be passive, okay? So what we need to do is have a very easy way to bring CPUs into this. We have to be able to continuously add targets. We need to be able to continuously update what we're going to fuzz when those targets change, things like that. We want it to be very simple because, as I've learned, if you have a large group of CPUs or you want to share CPUs with somebody else and you don't make it very, very simple, it's not going to happen, okay? People are going to take their machines back from you. They're not going to set things up at night to do the fuzzing that you've asked them to do. So ideally, what we'd like to be able to do is hand someone a VM and say, every night when you go home from work, hit the play button. Every day when you come in the morning, hit the pause button. End of story. We're all done, okay? So it's got to be completely automated on that side. Okay, so while we're doing this fuzzing in a continuous fashion, we'd like to be able to triage in a totally separate area, okay? So when we do this triage, we don't want to triage every single bug, okay? We want to be able to select for our understanding of the bug. And we'll talk about a little bit more on what that means and how it changes over time a little bit later when we really get into it. But what we'd ideally like to be able to do is get all the data we can out of the original crash so we're not replicating work, and have enough data for somebody to be able to say, I'm interested in type of bug X, Y, and Z. I understand it. I can work with it easily within my group. Let's go there and get all those bugs out of the database as they've been changing over time and go off and do our triage process, okay? So as far as attack surface analysis goes, what we need to do here is, especially for our dumb fuzzing, we need to be able to understand how much code coverage we're getting because that's our most important area. So we've got some tooling around this that we're going to talk about a little bit later, but this is absolutely our first step, okay? If we don't know how much code coverage we're getting, we're going to be wasting a lot of CPU time. So I would like to introduce the Miller theorem. I guess he's a doctor. He should probably have a theorem. I don't think he has a theorem yet, so I decided to give him one. It's pretty simple. As code path coverage goes up, you get more bugs. As the time spent fuzzing goes up, you get more bugs, right? Pretty simple here. More code coverage, more bugs. And so that comes down to our CPU efficiency. So obviously, we can add CPUs very easily. It's really cheap to do that. But our main problem here is that if we're not efficient in it, that time spent fuzzing is going to go down. No matter how many CPUs we have, we're reproducing work, so it's not useful, right? It doesn't actually go into the theorem because it's reproduced. Okay. So how do we obey that theorem? We have to be able to easily, in an automated fashion, select inputs to maximize code coverage. And we have to easily set up a framework that maximizes uptime. Okay? And those are going to be our two goals when we build our tooling here. So we've been talking a lot about mutation as something that's very human efficient, right? But of course you can do both, right? As you set up the first cycle of your mutation fuzzing, the people who set up your mutation fuzzer, who are starting to understand this format, need to begin building templates for their generation fuzzing, right? And those templates you're building for generation are going to be pushed back into your data set for triage later on. But there's no reason not to start mutation fuzzing while you're developing templates for generation fuzzing, right? There's absolutely no reason not to do it. It's been proven very, very recently that you can find a ton of bugs with very simple mutation fuzzing. And further, you can prove very easily that you're not reproducing work when you're doing mutation fuzzing, right? I can take my sample set, I can find my code path coverage, and I know that I'm exercising certain code paths, and I can stick to those, right? And it also means that later on, when I'd like to retest code when things change, I can go back to the same test cases for my mutation fuzzing and get that done very efficiently. So we really want to get away from that fuzzing as a single thing as opposed to an ongoing process. And the illustration of our ongoing process is essentially that we're going to run our tests. We're going to collect all the data for it. As things update and change, we're going to retest. And when we're talking about retesting and things changing, we're talking about patching, new versions of software, being able to easily determine what's changed, and go back and cover all of those different code paths as they come up. Okay, so the vast amount of time that we spend in fuzzing is going to be in the actual test execution itself, right? So we'd really rather not do a bunch of tests, collect some crashes, and then go back and do more testing on that to figure out what's important about it. What we'd like to do is catch everything that we can possibly catch that's important at that time, because that's going to be the majority of our time spent. So we'll talk about how to decide what we're going to grab and what's absolutely necessary to grab when we get into an implementation of the workflow. But for right now, what I'd like to just say is that you don't really want to run your tests in a vacuum. You want to have them be watched by something, right? Custom debugger, something like that. Okay. In order to make all this happen very easily, we're going to be required to distribute well, and so we're going to be required to have some sort of centralized management. Okay? And we'll look at what we need in the centralized management, what we should be storing, how to distribute pretty easily. Another thing that you'll see is people grab a whole bunch of crashes. They end up with crash dumps. They store their data like that, just kind of sitting around. It's very, very difficult to get through. And for the triage group that's going to come back and look at this stuff, it's really not useful at all. So what we're going to try to do here is store all of the data that we possibly can in a searchable database that we never, ever get rid of. Okay? Storage is cheap. We want to store it forever because, as we'll see,